Hello, and welcome to the video directions to assist with Lab 2 for Astronomy 20. In this lab, we're going to be learning about constellations and collecting some information about them. And I want to make sure that you're familiar with how to use the software and kind of understanding what I'm asking for. All right, so in the directions it says that you're going to include the requested information about Northern Hemisphere constellations. So these are the constellations that we would be able to see throughout the duration of the year in the Northern Hemisphere. Okay? Different than the constellations you'd see in, say, the Southern Hemisphere, like Australia or South America. Anyway, you're going to have a sketch. Okay, the constellation sketch should show the shape and location of the dominant stars, labeled 2 to 4 brightest stars. Visibility, describe what time of the year this constellation is most visible. Star details, list the brightest stars that were included in the sketch. This should include the distance to the star in both light years and parsecs, the star's spectral type and luminosity, and the star's apparent magnitude. So I'll show you where to get all that information. Then you're going to find Messier object details. Include a short description of one Messier object that is included in the constellation. Okay? There'll always be at least one. So I'll kind of show you some parts of Cassiopeia, but I won't show you the whole thing. And then the whole lab is just doing this for all the constellations that are listed. I think I might have 14. Let's see. 19. Okay? All right, so let's take a look at Cassiopeia. So the software that I highly advise using is Stellarium. You can go here and get the software. It says here Stellarium is open source free software. So it works on any computer. It's totally safe. So you can download it and run it on your computer. You can also just run it off of the web right here. Okay, I think that's probably the easiest way. When you open it up, it wants to use your location. I'm gonna I'll go ahead and say allow. Now I'm close enough to Solano College that I'll consider my location to be sufficient. I think that's going to apply to all of you as well, unless you are significantly farther away at your current location. Okay. All right. You could also get a mobile app. Okay, I believe that one is also free. All right, but the one on the web works just fine. All right, so one of the first things you want to do is turn on the constellations. So you have some options down here. You can turn on constellations. You can also turn on constellation art. That's not necessary. Let's turn on the constellations. This is what the art looks like. Okay, again, just kind of muddies up the picture, but if you want to take a look at it, it's kind of fun. Okay, so now let's go ahead and find Cassiopeia. Okay, so if we look, there's Cassiopeia. You can see over here, it did have a name in front of it. I'm going to zoom in a bit. I'm just using my trackpad to zoom. So here it is, Cassiopeia. It looks like an M. That's the way I always think of it. You can find it with the naked eye. It's near Cephus, which is a rectangle with a cone on top, or a triangle on top. So let's go ahead and zoom in on Cassiopeia. So one thing that I want to think about is when it is observable. Okay, so if we look right now, we have the clock as 8:46, so certainly after sunset. I believe that's kind of a default that it will automatically go to the day that you're at, so the 31st of August, but it'll progress the clock until sunset. Sunset right now is around 8:10, so it's doing a half hour after sunset. So it's kind of assuming the first time that you'd be able to see all these stars, okay, assuming no light pollution. But we can change that time, all right? And so we want to find what time of the year that Cassiopeia is visible, okay? And by the way, this would be the sketch. You do these stars. And actually, before I go on to visibility, let's zoom in a bit. Here are some of the brightest stars: Kaf, Shedar, Navi, and Rukba. Okay. All right, looking good. So what you want to think about here is the month, right? So we think about sunset, sunrise. We want to find again when Cassiopeia is visible. Okay, so I'm going to go ahead and progress by months, so we can see that in August it's definitely visible after sunset, right after sunset. But if we go back to July, okay, we can see Cassiopeia is down there. Okay, so as we go on, all right, so Cassiopeia is further down there. So what about as we go, into, right, there's Cassiopeia again, because it's kind of taking a track like this across the sky. The constellations don't just rise and set, in any arbitrary way. They're going to loop around. Okay, there will be some that are going to rise, kind of in the east and set in the west. But truly, the only time that all the constellations would be rising exactly in the east and setting exactly in the west, the only time they'd be all making perfect arcs overhead would be if you were located at the equator. And since we're not, many of the constellations instead swirl and they spin in those concentric circles about the north celestial pole. Refer to previous lecture videos for more on that topic. So here we see Cassiopeia again, definitely it's in here. These are longer days, right? As we go back into May, okay, into May, all right. So that's a good idea. Okay, so it's Cassiopeia again. Okay, now we're going back into February. Definitely visible at 8. Okay. December, November, right? So it's looping around, right? We're coming back around. September, we still have Cassiopeia at 8. Okay. And then back to August. Okay. So what is that telling us? Well, let's take a look, right? So let's go back to the time that it was, we're kind of right near the horizon on the longer days. So over here, right, in May. But what if I progress the time, right? So if I go, okay, by 11 it's up. Okay, 1 in the morning. So it's definitely risen, right? So that's all you're looking for. In fact, really, you don't even have to make sure that it's going to come up at some point, because the idea is that as you go through the months, all these locations of Cassiopeia are going to, let me zoom out a little bit, are going to be achieved at some point in the night in a given night, okay? And sure, in September at 4 in the morning, it's right there. In May at 4 in the morning, it's at a different location, all right? So let's see where is it now? Let's go back. I lost Cassiopeia. There it is, okay? So there's Cassiopeia, all right? So if we go back to May, right? It's again 4 in the morning. It's still in the sky above the horizon, just a different part in the sky. So really, by doing this whole month circle and making sure that it's visible the whole time of the year, right? So here in January, that's telling us, since Cassiopeia never has a month where it's below the horizon, that means that it's visible year round. That's because at our particular latitude, it is a circumpolar star. Okay, this would be in contrast to, where's a good example? Okay, so let's go over here to Pisces, right? So if I take a look at Pisces instead, notice this constellation right here. So I go up, Pisces is a rather long constellation. In May, that's fine, right? So you can see it, and as we progress into the morning, so basically we can see it just a little bit in May. We can see it just in the early hours of the morning, and only partially, right? And by the time the sun rises, you wouldn't be able to see it, so this would be the invisible constellation. But what if we went back, right? What if we go, let's go back to the actual nighttime. If I go back in 3 in the morning, right? Well, where's Pisces? Okay, let's see, so I check all the way from sunset. Okay, no Pisces, right? That's telling me that Pisces is only visible during the day, right? See, I think that it's coming up over there. Pisces is only visible during the day. There it is. Okay, there's Pisces again. During certain months of the year. The other way to think about it is just it does go below the horizon. Look, there it goes. It disappears. Okay? There's a time of the year, and we can again go to a certain time. Let's go to a time that's definitely nighttime. Let's go to approximately midnight. Okay, let's make this closer to midnight. All right. So we'll just go to midnight, just to drive home this point, and go back to my month switcher. So let's get Pisces to rise again, based on a certain month. There it is. Okay, there's Pisces. In this case, Mars is part of it. Mars is not always fixed to a particular constellation, because Mars moves independent of the constellations. But here, Mars happens to fall in the constellation Pisces. Right. So yeah, sure. In August, we can see Pisces. In September, we can. Right. In October, we can as well. November, sure. December, yeah, that works. Okay. But then it starts to disappear, right? So yeah, you'll be able to see it some of the night in January. But as we get up to February, no, Pisces is hidden. Now, first of all, that makes sense, because Pisces is one of the zodiac constellations, which means it is along the ecliptic, which means it's not going to be circumpolar. It means that there's going to be a time where it's on the other side of the sun. It's only going to be visible during the day, which, in other words, it's invisible to naked eye observation. Okay? So that would be an example where you'd have to think about the months where it's best to view it. Well, we know it's worst in February, so the months best to view it, if we go back, are the ones where it's highest in the sky, such as October or September, right? Those are great months to view Pisces. Okay? So visibility for Pisces would be dependent on the time of the year. Visibility for Cassiopeia, well, what do we see about it being circumpolar and never setting? Okay, so now on to star details. So hopefully that makes sense about how you can answer that question. Right? It's probably one of the more difficult questions, right? But I think it requires some thought and relation to ideas that we've that I've been stressing in the lectures. Okay. That's of course if you are taking a lecture equivalent to this class. So excuse me for those of you that are not taking a lecture as alongside of this lab, but those are still important ideas about circumpolar, ecliptic, all things that you would see in an astronomy textbook. Anyway, moving on to star details. All right, so list the brightest stars that were included in the sketch. Okay, so these are the ones that were the 2 to 4 brightest ones. So, and we're going to want their distance in light years and parsecs, spectral type, luminosity, and apparent magnitude. All right, so let's go back to our Cassiopeia. All right, we're just looking for that M. Zooming in on it. There you are, Cassiopeia. Okay, so we'll zoom back in. Okay, now I don't care about the time of the day or the time of the year or anything. I just want to make sure I can find it. All right, so let's get all our nice bright stars. Okay, so Navi, Cap, and Shedar. So let's do one example. So I'm going to click on Navi. I'm going to double click on it. Okay. So let's look at the information that we got. Okay. So here's some alternative names, more technical names for it. We have its magnitude, its distance, its spectral type. Okay. So that's the information you want. Okay. So we have its spectral type is BO. All right. I wouldn't worry about the rest of this. I just want BO. The distance, 549.09 light years. That's only one of the things you want. This is the apparent magnitude, the 2.19, or 2.13, excuse me. All right, so let's see. Is that everything that I asked for? Let's see. Yep, light years. I'll talk about converting the parsecs. Spectral type I already got. Okay, so we also want the absolute luminosity. Okay, so let's go down. I'm going to go ahead and open up Wikipedia because this will have the information. Okay, so notice there's always a link to Wikipedia for that star, so you can easily get the information here. And I think this way we won't even have to convert to parsecs. Okay, although I'll mention the conversion. Okay, so here's the parallax angle. We don't care about that, but there's the distance. All right, so you can see it's 550 light years or 168 parsecs. Okay, that's because a parsec, if I click on this, a parsec is equivalent to 3.261 or 3.26 light years. And what a parsec is it has to do with a star that has a parallax angle of 1 arc second. Okay, not a lot, but it turns out that that's one of the best cases you can hope for a parallax angle. So the closest stars are just about that far away, a little bit further away. So that means the closest stars have a parallax of just under 1 arc second, which is why ancient astronomers were never able to discover that parallax because it's too small to measure with the naked eye. Easy to do with the telescope, but nearly impossible with the naked eye. Okay, and you'd have to find that one star in the sky that even has that much. Most would have much less, such as our Navi star. Okay, and you can see here's the alternative name, Gamma Cassiopeiae. All right. Also, informal name is Navi. You can kind of think of that as the more interesting name. So when we get down here, here's the absolute luminosity, 34,000. And what's the unit? Well, solar luminosities. So that means the actual power output of the star is 34,000 times brighter than the sun. Okay? Does that mean that it appears 34,000 times brighter than the sun in the sky to us? Of course not, right? It would blind us, right? But that's its actual luminosity. Okay? The units there would be watts. It's actually power or joules per second. Okay? But it's relative luminosity because it's measured relative to the sun. Okay? Just a different unit. But what about its brightness, right? Well, we saw that before, and we go down here and we have its apparent magnitude. Okay, so let's see. All right, surface gravity, we don't care about that. The apparent magnitude wasn't the other one. I just wanted to see if it shows up. There it is. The absolute magnitude, negative 3.98. Okay, make sure that's what we saw here. All right, so we saw 2.13 as the magnitude there. So I would prefer if you give me the apparent magnitude as given on Wikipedia. So go ahead and navigate over to Wikipedia. There's similar scales, but this is the one I want to become more familiar with. Okay, so all right, so on the inverse logarithm scale, measure the luminosity of a celestial object Object's absolute magnitude is defined to be equal to the apparent magnitude that the object would have if viewed from the distance of exactly 10 parsecs. Actually, I do ask for the apparent one, so never mind. We want the apparent magnitude. Here it is. Okay. So the absolute magnitude is actually directly convertible to luminosity. It's just going to be another way to think about how bright it is, and it's at a assumed fixed distance. Okay. All right. This is power. This is how bright it would be if you were 10 parsecs away. But we're not 10 parsecs away. In fact, we know we're 168 parsecs away from this particular star of Navi. So we want the apparent magnitude. So let me quickly explain the apparent magnitude. So the idea of the apparent magnitude is probably best kind of summed up on a table like this. Okay. So if we have a negative apparent magnitude, so that's number of stars other than the sun brighter than the apparent magnitude in the sky. Okay. So there's only one star that's this bright, that has this negative level of apparent magnitude. And let me show you if so the example of the sun and the moon. So the sun, okay, we go down here. So sun appears about 400,000 times brighter than the moon. So we see here that the sun has an apparent magnitude of negative 26.74. That's the brightest thing in the sky. Okay, the full moon has an apparent magnitude of negative 12.74. So the idea is the larger the negative number, the brighter the star is. Very few objects have apparent magnitudes that are negative. Some of the planets do, obviously the moon and the sun do. And also this is a logarithmic scale. Okay, I'm not going to ask you to calculate the logarithms, at least not in this lab, but it's worth noting that the difference between an apparent magnitude of negative 26.7, very bright, and the moon, negative 12.74, you might think, oh, well, that just means the sun is about twice as bright as the moon. Well, of course, that's not true. The sun is way brighter than the moon. And we look and we actually carry out the logarithmic scale, and we find out that based on the fact that these are powers of 10, the actual brightness in terms of a multiplication factor is 400,000 times. So the sun is 400,000 times brighter than the moon. That's what this logarithmic scale means. Okay? It's a different way of scaling things. So the point being then that only the very brightest stars, like Sirius, have apparent magnitudes that are negative. Okay? So there's only one star. Sirius has an apparent magnitude of negative 1.46, the brightest star in the sky other than the sun. Okay? There are a few other stars that fall into the category between 0 and negative 1, so they'd have apparent magnitudes of, say, negative 0.5. Okay? So those are going to be the very, very brightest ones, like Vega. Okay? But then as we see, there's a lot more that are much dimmer. So then Navi, if we go back, had an apparent magnitude of 2.47, which means it's bright, but not in the brightest category. So one last time, let me show you. So falling into the 2.47, that's in this category. All right, so that means that it's one of 171 stars, right? So it's in the top 200 brightest stars in the sky. Okay, because anything under 3 is going to be the brightest stars. I know it seems backwards, but that's just the whole idea of log scales. Right? So anything under 3 are the brightest stars, and definitely visible to the eye, because we can see that there is about 9,100 stars visible to the eye. Anything with an apparent magnitude of less than 6.5, and that's assuming best conditions for stargazing. Really, you're more likely to find anything with 4 or less. Okay, so kind of neat idea there, because it gives us an idea. Should you be able to see this with the naked eye? Well, in this case, yeah, you should be able to see Navi with the naked eye. In fact, let's go back to Stellarium and zoom out a bit and look at maybe one of the less bright stars in Cassiopeia, like this little one over here. Click on it. Okay, go to its Wikipedia. Check it out. It's got an apparent magnitude of 3.37, so still visible, but much fainter. Because again, the difference between 2 and 3 are going to be not 400,000, but well over 100 times different in brightness. Okay. All right. So there you have the information that you are asked for. Apparent magnitude, absolute luminosity, okay? And give me the luminosity in terms of the L naught, as I showed you in Wikipedia, okay? The L with a little symbol with like a circle and dot through it instead of absolute magnitude. Again, they're interchangeable, but I prefer if you give me luminosity. Spectral type, you saw that, okay? And then distance and light years and parsecs, you can pull both of them off of Wikipedia, and I already explained the conversion between the two. All right. Let me say a bit about spectral type before I move on. Okay, so we'll go back over and look at an example. All right, so here we have this this other star in Cassiopeia. Doesn't seem like it has such a common name. All right, and we'll go down to spectral type, B3V. Okay, so this is kind of the best example of spectral type. All right, this when there's not extra information here. Stellarium will sometimes have all these, extra decimals, getting really into the details. But B3V is great. Okay, or really B35. So let's look at what that means. Okay, so B refers directly to the temperature of the star, which also tells us its color, tells us that star is bluer. Okay, and then the 3V is going to be a classification within that segment. Okay, it's going to tell us kind of what type of star it is, whether it's on the main sequence, whether it's like a red giant, or so on. Okay, so we can see here that the V, which really is the Roman numeral 5, tells us that our B3 star is a main sequence star. Okay, so in fact, let's go back to our first one. Go back to Navi. All right, Wikipedia. All right, go down. Okay, what was the spectral class on that one? So that one has a B, it has a 0.5, but it also has the Roman numeral 5. What does that tell us? Well, it tells us again that it's a blue star. All right, but then the fact that it's type 5 tells us that it's main sequence. And again, that's primarily what I care about, the letter and the Roman numeral. Okay, because if it had a Roman numeral of 4, that's a subgiant, right? Roman numeral 3 is a giant. Roman numeral 2 is a bright giant. So there's different categories. 1B is a supergiant. 1AB is an intermediate size supergiant. Okay, and then we have a luminous supergiant, and then we even have hypergiants. Okay, they're very rare. All right, there's only a few of them, like Cygnus OB2, pound 1-2. Okay, so hopefully you get the idea. And I didn't go too much in the details, but I think they're interesting and really kind of make you think about the data that you're collecting. So very last thing is the Messier object. So what's that? Okay, so let's go over and let's find one. Okay, so we need to find a Messier object within the constellation. Okay, so what I want to do then is I want to turn on Messier objects. So we want them, okay, so deep sky objects. So these ones right here. So I turn it on. Okay, so any deep sky object is a Messier object. And you can see they clearly get illuminated, sometimes by like a solid circle around them or a dotted circle. Now, they don't have to be within the lines of the constellation, they just have to be in that section of the sky. Because the lines of the constellation, they just represent the kind of the picture, but then the sky itself is broken up into these puzzle piece rectangular shapes that surround the connecting dots of the constellation itself, of the picture. Okay, so anything near the constellation would be a Messier object that meets the standard that I'm looking for in the lab. So let's look at this one because it's nice and bright. Right, so there it is, the Pac-Man Nebula. How cool is that, right? And let's see what information I want. So include a short description of one Messier object that is included. So just the one. So if I wanted the Pac-Man one, I would go here. Going to Wikipedia is a great place to go. Okay, we get a nice picture of it, taken probably with the Hubble telescope. All right, and using the classic Hubble palette. This is kind of like how they add artificial colorization to the nebula. But it's a nebula. You can read a bit about it. And I just want a 2-sentence description about the fact that it is a nebula, maybe where it is, and so on. The other common type of Messier object that you're gonna find, which Messier object is just technical term for deep sky object, is a galaxy. So they're either going to be nebulas or galaxies, primarily. Okay, so hopefully that sums it up well, and you're just going to rinse and repeat and do that 19 times to get a good kind of pass of looking at the sky and appreciating all the things that are out there. Okay? All right, well, thank you so much for watching this video. I hope it's been very, very helpful. Send me messages or emails for any follow-up questions.